Hello, everyone, and welcome to the next lecture of our master's course at MIPT in the modern C++. And today we are diving into one of sometimes puzzling parts of the C++ programming language, template specialization. We all know templates allow us to write generic code, but what happens if the generic version isn't good enough? What if, for a specific type, you know a much better, faster, or more optimal way to do the job? That's where the specialization comes in. It's our tool for telling the compiler, for most types, use this general recipe. But for this specific case, use my custom hand-tailored version instead. And today we will journey from the automatic behind the scenes implicit instantiation through the explicit commands we give the compiler all the way to the powerful technique of so-called partial specialization. We'll uncover the precise rules the compiler follows to choose the right implementation and generate the final code. And let's start again with the normal semantic process. 2 lectures ago, we introduced this notion, and let's walk through the normal process again. This process consists of several key stages. Consider this overload set, and say you are just calling min of 1, 2, 3. What happens? First, overload resolution jumps in and looks up the name, what min can be, and when overload resolution when name lookup finished, overload resolution chooses the best of viable candidates using implicit conversion sequences, of course. And then next is type deduction, which encompasses both deducing the types and performing type substitution. Here we reduced int and then substituted int here. And finally, we arrive at the core of the process, template instantiation. It's worth noting that elements like type aliases are resolved really early, very early on, and aren't shown in this diagram like it's start of name resolution. And name resolution is combined term from name lookup and overload resolution, and type deduction is combined term from type deduction and type substitution. And so the flow is name resolution, type deduction, template instantiation, and now min function starts instantiating, and it needs to look up what this name means again, because now this name is bound to another entity. And this leads to important question. What do we mean by instantiation? Please think about this a little bit yourself, because maybe you will come up with some interesting ideas. So what instantiation really is? Okay, and the correct answer is instantiation is the process of creating an instance of a specialization. This is good definition. It's helpful because it connects two terms that can seem distant. Instantiation is a process, is the process, and the specialization is the concrete outcome. And you may either generate it or make it manually. And let's look here at our min function. We have a call to min of 1 and 2, and here we can see our normal process at work simultaneously. We found the name, we've deduced the type, and we've performed the type substitution. And the next step is to generate specialization. This happens somewhere here and there, somewhere between after the point of declaration and before the point of specialization. And this is what we call implicit instantiation. It's called implicit because it happens automatically on demand, so-called lazily. The compiler only generates the code for specialization of this template of type int when t equals to int when it's actually needed. And you can call this min function with integer arguments again and again and again later in the same translation unit, and the compiler will not instantiate it a second time. It will see that the declaration has already been generated and will simply reuse it. However, if you call it in a different translation unit, where the previously generated specialization is not accessible, the compiler will happily instantiate it again. This is perfectly fine and nothing bad will happen. So, besides implicit instantiation, we also have explicit one. And let's review the syntax. This declaration, extern template, and then some specialization syntax means we are suppressing the instantiation from this point to the end of the translation unit. It's an explicit prohibition. This is not erasing the specialization. It's a promise that it has been instantiated elsewhere and the linker will find it. And this declaration, template without extern, is very different thing. This declaration is explicit request to instantiate right there. And this technique is primarily used to control object file size by explicitly instantiation heavy template in one source file and then use an external declaration in others. You avoid the cost of instantiating it in every single translation unit. Of course, this relies on the linker. If the linker doesn't find the promised instantiation, we get an unresolved external symbol error or ill-formed no diagnostic required program. So it's better if the linker does, in fact, find it. Let me show you a quick example to illustrate this. I've set up a multi-module program in Godbolt to demonstrate how this works in practice. So let's consider our multi-module program. We do have some library. One library is maxuser1cc and second is maxuser2cc. And what those files do, they both are just using some template function max here and there. And consider those libraries are huge and consider this function is huge. Some huge template function or class with a lot of template function resides in this header max hpp. And this header file declares and defines this max function template. And now in main.cc we are using both foo and barf. And in our CMake list we are adding one library, adding second library, adding main, and then we are linking libraries and we are done. And post build we also reading symbols. And what will we see in the console? Okay, in the console we will see this is one library, libmaxuser1.a, and we can see this symbol. And this symbol is weak symbol of a function max, which was instantiated here. And in second library, this symbol is function max that was instantiated here. And you might see that compiler also generated special section for this function, and this special section indeed for merging. And when linker merges this together, you will see only one of this in the resulting binary file. But we do have two huge libraries on our hard drive. Imagine this is not 7 bytes, and here we have 8 bytes, 8 bytes long. Imagine it is 8 gigabytes, and you don't want to have two 8 gigabyte functions on your hard drive, okay? And so what will you do? And here you will explicitly control instantiation. We are adding third library, and in this third library, max.cc, we are forcing instantiation. Here we forced, please spawn this function template code for int just here. And for all other translation unit, including max.hpp, we are blocking instantiation. We are blocking it everywhere, and we are forcing it here. And you can see, even if you explicitly blocked, you may explicitly force. And now we will not see any implicit instantiation here because it is blocked. And we cannot see explicit instantiation here because it is blocked. And if we will see in our symbols again, what we will see undefined label to the max function instantiation here and undefined label there, and it with its section is defined for max library only. This is really powerful technique. I'd like to take a quick step aside from the main topic because I find this next point quite fascinating. So let's consider this scenario. We have two dynamic libraries, lib1 and lib2, and we link both of them to our main program as a shared libraries. And the function bus is called both from foo and bar inside these libraries, like max in previous example, okay? The question is, for the static variable t inside our template function bus, will there be one single copy of t shared across the program or two different ones? Please, imagine you are on the job interview. Pause the video now. Try to figure out the solution. 3, 2, 1. And the proper answer, it can be either. It depends. Let me show you. And it depends on something that is not even a part of language. It depends on toolchain. So, okay. We got this example. Maybe I got it here as well. Yes. And we got this example, lib1, lib2. And now we do have shared libraries, as you see. Do you see it? They are shared. And we link them as previous. And we are reading symbols from shared libraries, which is also okay. And we have this bus function. And this bus function just returns address of static global variable t. And now, in main function, we are calling foo from one shared library, bar from another shared library, and just check if results are same or different. And in this case, if we will see in our executor, we do see inside this dim section the t variable. This is mangled t variable. You can demangle it to convince yourself it is so. And here we do in the dim section of second shared library, we also can see the t variable. Okay, and what is the result? And the result is same. They are both exported. They are both exported as unique symbols. And they are indeed unique, and they are the same symbol. Linker used section information to merge those symbols even though they came from shared objects. And then why I said it depends? Okay, because it depends. Let me make those variables different. I just add visibility hidden to remove this t variable from dim sim. Because this bus function is inlined. It is not in dim sim. But it like propagated its visibility to this static variable. And if I am placing visibility hidden here, then what will I see in the executor? As executor, I will see nothing aside of foo in dinsim, nothing aside of bar in dinsim, and addresses are different. You may look here and convince yourself they are different. And this was always pure magic for me. How template instantiation really works, what really means to instantiate a temple, how linkers love to merge symbols, how compilers assist them in every possible way. Okay, let's go further. And let's move on to explicit specialization. This is another option we have besides letting the compiler instantiate templates for us. Because if the compiler is instantiating template for us, it cannot write different code inside it. And if we are doing this, we can write virtually everything. We can make specialization of max function for int like, I don't know, format your hard drive, so on, everything you want. I guess you want to format your hard drive, okay? And this is primary template for max, and these are its explicit specializations for int and float. And now crucial rule. A specialization must be declared in some sense after the primary template. Or to use more precise term, the primary template must be reachable when the specialization is declared. And on the next lecture, we will touch upon what is reachable and how it corresponds with physical code organization in your program. And that's why this example is an error. Because the specialization comes before the primary template is even seen. And for now, just remember the simple rule. Primary first, then specialization. We'll dive deeper in future. Okay, and now let's look at the formal rules that govern how all the species, implicit instantiation, explicit instantiation, and explicit specialization interact. The standard gives us three main rules. First, the explicit instantiation may appear only once in the entire program. Second, an explicit specialization also may appear only once. And third, an explicit instantiation must come after any explicit specialization for that same template and type. So the correct order is you have your primary template, then you can write an explicit specialization, and only after that can you force an explicit instantiation. If you violate those rules, your program is considered ill-formed, no diagnostics required, which means the compiler isn't obliged to give you an error, but your program is invalid. This leads to a subtle question. How do you think an explicit instantiation suppression interacts with an explicit specialization? And let me, on the next slide, show you some examples, and then I will show you an example what will happen directly. Here we provide an explicit specialization for double, and when we call this max double in foo, it uses our custom function. It uses this function that always return 42. Remember, we can write everything in the code. This is the difference. And it is perfectly fine. No implicit instantiation happens here anymore. And I may remove double and rely on type deduction, and no implicit instantiation will take place anyway. And now for maxint and bar, the compiler does implicit instantiation, and then we are trying to provide an explicit specialization for it after the implicit instantiation has already occurred. And this is ill-formed. You cannot specialize something that has already been instantiated in the translation unit. The rules require that a specialization must come before any instantiation for that type. And let me show you an example. Example is, we do have a primary template here, and consider first early equals 0. And if early equals 0, we just forget about the slice. And we have a primary template, and then we do have an explicit specialization for it. And here we do have forbidden forbidden instantiations. We explicitly specialize and we forbid any further instantiations, and it is perfectly ok. This function call is bound to this explicit specialization. And it's great, but what if we do vice versa? So I may assure you all tests are passed. Yes, everything is correct. And what if we will do vice versa? What if early equals 1? And if early equals 1, we are saying now implicit instantiations are prohibited, and we are doing explicit specialization, and it looks like it's okay. We prohibited implicit instantiations to safely, like in safe-ish manner, do our explicit specialization and not conflict with implicit ones. But this is not a prohibition itself. This is a promise. And it is a promise that implicit instantiation was generated above in some other translation unit elsewhere. And if it is already generated, you cannot do it manually. And this is an error. And error is quite interesting. Explicit specialization of this after instantiation. We don't know the point of instantiation. All we know from external template syntax is that instantiation already happened somewhere and it is enough. Okay, now I guess you understand. The rules are really simple. If you did something manually, then trying to generate it will just bind to your manual definition. If you already generated something, then trying to do the same manually is an error. This is really simple rule of thumb. And another useful form of explicit specialization is deletion. Deletion is a subclass of explicit specialization. Imagine you have a template function that works for all pointers, but you want to explicitly forbid its use for certain types like char pointer or void pointer. You can do this by providing an explicit specialization and marking it as equal delete. Now, here's an interesting thought experiment. What do you think happens if the compiler has already implicitly instantiated a specialization for char pointer, and then it encounters this deleted specialization later? I will not show you the answer. Please download this presentation, click on this link. But before doing this, please try to read the standard, understand the rules, and try to figure it out yourself. Okay. And now, all right, moving on to non-type parameters. And the key idea here is that these parameters must be of what's called a structural type. This is a very specific term from the standard, and its definition is tailored to allow the compiler to work with these values at compile time. The basic intuition is simple. Everything must be known at compile time. Structural types include scalar types, okay, This was relaxed in C++20, so except floating point is little obsolete line on this slide. LVarue references, structs whose field and base classes are public and not mutable, and where every field is itself structural, or an array. Okay, and how do you think? Can you perform template specialization based on this non-type template parameters? And yes, definitely, definitely, you absolutely can specialize using non-type parameters. In fact, it's very useful. Look at this example. I have a function that precedes an array of any length, and any compile time no length, say to sort it. I don't know. But for a very specific size like 3 elements, I can write a much more optimal specialized sorting algorithm. So here I've specialized for exactly 3 elements and provided that optimal implementation. And this principle extends to other non-type parameters as well, like pointers, references, structural types. Just remember that an array template parameters decays to a pointer just like it does in regular functions. And you may also click on this link and see some fascinating examples. Let's not spend our time on this. Okay, and we also have template parameters. And this is when a template parameter is itself a class template. As you can see, this is a template. And its parameter of our print size function template. Inside the signature, we can even instantiate it with this type, like element type. And for now, this might seem like a complication. You might wonder why not just take some type container directly. And I can understand you. I also think this is some kind of overcomplication, but we will come back to this technique later. And of course, as you already guessed, you can specialize based on template parameters. And this is a link. Please click on it and see how you can do it. This is really exotic technique. Let's also not spend our time on this. And let's return to our semantic processes and discuss how all of this interacts with type deduction. Everyone remember this from last time, right? We recall how the compiler decides which overload to pick when multiple templates match. Both templates here, this and this one, match the call foo of address of X, but template number 2 is chosen because it's more specialized. This is resolved through template argument deduction, cross here and there. If you don't remember this, please go and see once again the previous lecture. Explanation was here. Okay, and this is resolved through template argument deduction. And now let's make it slightly more interesting. Let's add specializations to these two function templates, and this is where it gets really intriguing. Okay, here's the crucial point. Specializations do not participate in overload resolution. Overload resolution only looks at the primary templates of free functions. So the first question is which primary template wins? And we know the answer. Template number 2 wins because it's more specialized. And now the real question is which template does specialization number 3 belong to? Does it specialize number 1 or number 2? This is one of my favorite examples. And please pause the video now and try to think what's answer here. And answer is interesting because I have a somewhat like zoological analogy to explain it. So 3, 2, 1. Okay, let's go to the natural selection. The key point is it's meaningless to ask which primary template the specialization belongs to in advance. The specialization is written for the function foo of int star, and it becomes the specialization of whichever primary template wins the overload resolution for the specific function signature. And here's a way to think about it. Imagine the specialization as a female deer. She comes into a clearing and sees two male deer, our two primary templates, who are about to compete. They perform cross-type deduction, lock antlers. I'm not an expert on deer behavior, but the one that wins, the primary template that wins overload resolution, is the one she chooses. Similarly, the specialization, it attaches itself to the winner. This leads to some interesting zoological nuances. The female deer can arrive at the clearing too early. In this case, she arrived when there was only one male present. She had no other choice, so she became his specialization. Now, the call foo of address of X will use template number 3, even though specialization number 2 looks like better match. Template number 3 won the overload resolution after the specialization was bound with primary template. And he won overload resolution, but it was too late for him. The female had already chosen the other one. This is the life. And now let's do a quick check to make sure everyone is on the same page. We have 3 templates again. The call is foo of address of X of address of X. It's a simple question. Pause the video now and choose your option. 1, 2, or 3. Simple like this. 3, 2, 1. Okay, and probably you think that answer is 3. But really, answer is 2. And why is that? Let's go back to our clearing. The female deer arrives and sees 2 animals, a deer and a crocodile. And she cannot be a specialization of the crocodile, which is template number 2, because her signature is not exactly the same as his. You can see here T equals T, and here T is not equal to T star, and here int star is equal to int star. She sees a male of her own biological species and a male of a completely different species. So who do you think wins in a fight between a deer and a crocodile? The crocodile, of course. The deer doesn't stand a chance. And this is very subtle trap. Here, of course, crocodile wins. Answer is 2. And very subtle trap is you must always carefully check that your specialization is actually a valid specialization for the primary template you intend it for. In this case, specialization number 3 can only be a specialization of the first primary template. But overload resolution picked the second one, the crocodile. Since the specialization isn't compatible with the winner, it's ignored, and the primary template number 2 is used. I must say I really grew to love this picture. This was about 7th or 8th attempt from the AI generator, but the result was worth it. Notice that the crocodile has already made its choice too. Okay, and this leads us to broader discussion. We've seen how instantiation interacts with overload resolution. But what about name lookup? What other rules or interesting edge cases do you know about how template instantiation interacts with name lookup? So let me tell you about two-phase name lookup. I teach this to second-year students as well, and this is master's course, first-year master students. And how do we usually explain two-phase name lookup to newcomers? We tell them there are two phases. Phase 1 happens before instantiation. The template undergoes general syntax checking and non-dependent names are resolved immediately, and this illegal name is non-dependent. If it's truly illegal, the compiler will catch it right here even if we never instantiate the template. Then comes phase 2, which happens during instantiation. This is when special syntax checks are performed and dependent names are resolved. This name, illegal name, is dependent on the template parameter t. Of course, t is part of this name. It's qualifier. Its lookup is postponed, and this leads us to the golden rule of two-phase lookup, the one I make my second years memorize for the exam. Let me remind you of it, or maybe someone can recite it to me. Okay. Well, it's written on the slide anyway. The resolution of dependent names is postponed until substitution. You need to know this rule as instinctively as you know about virtual destructors. If I ask you, the answer should come in under 10 seconds on my clock. But is it really that simple? Well, drilling this into students is one thing, but the reality is a bit more complex. And now we are going to dive into that reality. First, let's get a clearer picture of what we mean by dependent names, because it's not just any name. The core idea here is simple. The compiler needs to know what you're talking about. But with templates, some names are clear from the start, while others are complete mystery until you provide a specific type. The name is dependent if its meaning is tied to a template parameter. Look, x. What is x? Is it a type, a static variable, a function? We have no idea until we know what t is. And the same logic applies to p arrow f. What is f? It all depends on the type of p. So the intuition is that the compiler can't know what these things means until it substitutes the template arguments. Now, this last example for y is the most subtle one. Here the name foo itself is not dependent. It's a normal function name. However, the expression for y is type dependent because the argument y has the dependent type. This means which foo gets called might depends on the type of t due to function overloading. So, while the name is resolved in the first phase, the final decision of which specific function is called is postponed until the second phase, when we know the exact type of y. And let me show you the TS problem. This is classic example. For those of you who took my second year course, this should be a familiar and straightforward puzzle. The code might seem tricky at first, but the answer becomes clear if you carefully apply the rules of two-phase name lookup. So here is a challenge for you. Let's apply our golden rule from the previous slide. Pause the video for a moment and try to deduce what will be printed on the console. Once you have your answer, continue to the next slide to see if you were right and to understand the why behind it. 3, 2, 1. Okay. The output is TS. And here is a breakdown. Okay, this is the TS problem, of course. The output is TS. And here is the breakdown. Inside call foo, the first call is for x, and x is non-dependent, and this resolves immediately here. and prints t. Okay. Here t is dependent, resolution is postponed, and here it resolves, and we can see also 4fs, and here 4fs is much better, much than 4t. And this is visible at this point at chosen and prints s. And everything's fine if you are a second grade student. But let's somewhat change our up. Oops. Now s is just int. And suddenly the output is tt. And it's a classic plot twist moment. When you think you figured out the rules, the situation changes completely. So why tt now? At first glance, it seems like nothing should have changed. The first call, 4x, is still non-dependent. The second call is still dependent. Even if s is int, this is better much than a template here. So what's different? And when your old theory can't explain a new experiment, what does that mean for you as scientists or future scientists? It means we need a new, better theory. And let me explain what's really going on here. So, what does two-phase name lookup really mean? Because in reality, it's not exactly what we teach to beginners. The real secret is that dependent names are actually looked up twice. The first lookup of foo of t happens during the first phase, where it finds our primary template foo of t. But then, during the second phase, at instantiation time, the name lookup for this dependent name is repeated. And for this second lookup, the compiler reuses, you won't believe, but it is argument which is dependent, so it is argument dependent. Compiler reuses the argument dependent lookup mechanism. And we've already seen how we use type deduction, and now we're using ADL. And we are using to search through what the standard calls the associated entity namespaces. So what is associated entity set? It's defined for the types involved in the function call. For fundamental types like int, associated entity set is empty. For a class type, the set includes the class itself, all its base classes, and any enclosing classes. And for templates, it includes everything associated with its template parameters. And the namespaces that contain all these entities are called the associated namespaces. So, we are building the list of associated entities, and for each entity, nearest enclosing namespace is associated namespace, and ADL at its core is essentially a lookup performed within these associated namespaces for given function. So to put it all together, the second phase of two-phase lookup performs an unqualified lookup again, but it also performs an ADL-based lookup into the associated namespaces of the template arguments. This is how it can find better matches that weren't visible during the first phase. So let's see what practical consequences this has. Look at this code. We have foo_int, a template function, and the bar that calls foo_t, and here foo_double, and here the instantiation bar of 1.0. And probably this looks better, but we are calling 1. We are calling foo_int. The call foo_t is dependent call. It will be looked up again in the second phase. However, the associated set for the fundamental type double is empty. So it is looked in nowhere. This means that the second phase lookup won't find our new fourth double function. It doesn't belong to any associated namespace of double. Therefore, the lookup falls back to what was found in the first phase, the fourth int function, which is chosen through the standard conversion from double to int. So the value of t will be 1. You can click over to Godboard and see for yourself that this is indeed what happens. Now, if we use a struct x and define fourth x, the value of t becomes 2. See, here it is 1, and here it is 2. Here it is 1, look here it is 2. Why? Because the associated set for x includes x itself. And when we reuse ADL mechanism during the second lookup phase, it searches the associated namespaces, which in this case includes the namespace where x and our fourth x are defined, the global namespace in this case, and finds the perfect match. This is perfectly logical, but it can also be incredibly frustrating because, let's be honest, we would love for these to work with built-in types as well. Because why the heck we are calling fourth int here? So, fellow C++ enthusiasts, how do we hack our way out of this? Any ideas? Pause the video now and suggest any ideas. 3, 2, 1. Okay, we can handle this quite easily using stud type identity, which has been available since C++ 12. Stud type identity is basically an empty type with no contents, no state, 1 byte long, which just carries the type on it, like int foo of int and stud type identity of int. This seems redundant, but it's crucial. Stud identity is a class type, and for class types, the associated set is not empty. And now, when the compiler performs the second phase lookup, it searches the associated namespaces of all argument types. This includes the namespaces where stud type identity and our two overloads are defined. As a result, the compiler finds our fourth double and stud type identity double, which is a better match, and the call correctly resolves to print 2. Think of it like this. We are giving the female deer a specific scent to follow this stud type identity T that reliably leads her through the forest of associated namespaces, ensuring she finds the right male deer, even for fundamental types. And you may experiment with AI-generated pictures and generate this picture and post it in the comments for this video on YouTube. Okay, here's a little puzzle that reveals a missing piece in our understanding. We have an incomplete type S and a wrapper template that holds t by value. You see this? And we have a function foo that take a reference to wrapper template, which is perfectly fine. You can have references to incomplete types, but we also have a function get that returns a reference to wrapper of S, which is also perfectly fine. And now the puzzle. This fails to compile because S is incomplete. And this compiles okay. What do you think makes the difference? You're unlikely to guess the answer right away, but it follows directly from what we learned 2 lectures ago. It seems we didn't do our homework from that lecture thoroughly enough. The answer lies in the subtle rules of name lookup and how they interact with incomplete types during template instantiation. And the explanation is, I would say, surprisingly simple. By the language rules, the compiler is forced to instantiate a template if anything in the lookup process could depend on that instantiated type. In the case of an unqualified call like foo of get, ADL might need to search through the associated sets. And since wrapper of S depends on the incomplete type S, this triggers instantiation which fails because S is incomplete. And for qualified lookup, like this, colon foo of get, this rule doesn't apply. The qualification prefix explicitly tells the compiler to not use ADL. Remember, ADL is a subroutine of unqualified name lookup. It only performs a lookup in the global namespace, finds our foo function, and sees what the argument type is valid for reference, even though S is incomplete. No instantiation is required, so the code compiles, which has fascinating consequences. Sometimes being explicit with qualified lookup can avoid forcing template instantiation that would otherwise fail. I think it's like mind-blowing. And this is a classic example and one of my favorites. How many of you have ever put a static assert of false inside a template intending it as a guard only to have the entire program fail to compile immediately? This happened because the condition is non-dependent. This is non-dependent name. So it's checked in the first phase before any instantiation. And the standard fix for years was to make the condition dependent by wrapping the false in a helper template. This forced the check into the second phase, so the assert only fires if the function is actually instantiated. But, and here's the fascinating part, this is a perfect example of the language retroevolution. In 2023, the Standard Committee decided this first example should have worked all along, even in C++11. So now the behavior depends on your compiler version. A recent compiler will delay this error until instantiation, because in C++11 standard in 2023 was introduced this hack. Ignore this for static assert. It shows how the lava of language standard can shift, sometimes invalidating old workarounds. Let me show you the example of this. The example is quite simple. So where it is, and it is here, I believe. The example is quite simple. We do have this false protector, and we do have static assert of false protector, and we do have template instantiation, and look here, yes, static assertion failed here. Okay, it failed both ways. It failed here and it failed there. And then I removing instantiation, and if instantiation is not happened, it will not fail. Okay, in GCC 15, everything is correct. But if I switch to GCC 12, I don't believe I'm doing this. Oh, my goodness. If I switch to GCC 12, then lava of the language standard will shift back and bury you. This is the output. You can see in the output of the compiler, sorry for this, yes, here. You can see in the output window that this static assertion failed even without instantiation. Even without instantiation, this failed and this didn't. So in GCC 12, it was perfectly right. For C++ 11 of 211. And GCC 15 is perfectly right for C++ 11 of 2023. I cannot believe I'm saying this. So let's summarize. We have both overloading and specialization, and when is one better than the other? The key advantage of specialization is that it lets you avoid dummy arguments. On the other case, specializations don't participate in type deduction. And these are valid arguments for using either overloading a function or specializing a function. But for function, you do have both. Not for types. For functions, you do have both type function overloading and function specialization. But types cannot be overloaded. So, how does this limitation shape the way we design with templates? And how do we work around it? Okay, types can be overloaded. Imagine this classic pre-C++ 17 problem. Since C++ 17 we have more elegant solutions, but back then this was a common challenge. We have a chain that inherits from T and from the remainder of the chain. We need to close the recursion, ideally for the empty pack, by simply inheriting from T. Then make chain returns this inheritance chain. And it doesn't work. Who can make this work by adding just 3 characters to the code? And first, let's understand why it fails. From the language's perspective, we are trying to define a primary template here with a different number of template parameters. This one has a parameter pack, and this one has a single parameter. Types cannot be overloaded. This is syntactically incorrect. Semantically, it's like fine, but we know what we mean here, but we can't do this by language syntax. So how do we fix it? Pause the video now and see if you can figure out 3 characters that will make this code valid. 3, 2, 1. Okay. And the solution is specialization. Since we cannot overload types, we use a different mechanism. We declare a primary template and then we provide what we will call partial specialization for the different cases. And now it works perfectly. But what is this? How this partial specialization work? And before we will come to how it is it really working, we need to see some more fundamental concepts. And the fundamental concept that will be crucial for understanding class specialization is point of declaration. Consider there's 2 code fragments. They both look questionable, and you should never write code like this, but they illustrate a crucial rule. In the first case, int y equal y, the variable from the inner scope is used for its own initialization. And this leads to undefined behavior. Why? Because, by definition, point of declaration is where the declaration ends. And the declaration of y ends here, and this is an initializer, and declaration of this y ends here. And this name is available at the point of declaration, from the point of declaration to the end of scope. And this is the same name. And here for this array, and this is variable length array, it is forbidden by language standard, but here this name is used from the outer scope. The point of declaration here is after full array declarator, x square brackets x. This means that x inside the brackets is used before the inner x is declared, so the compiler looks to the outer scope and finds the outer x. The core rule is before the point of declaration the name is not yet introduced, so the name from the previous scope is used. This subtle rule is the foundation for how we'll understand the lookup rules in template specializations. When we write class templates, unlike function templates, the point of declaration is crucial. For class templates, point of declaration is right after the class name and its template parameters. Once the POD has been reached, the name, in this case FW node, forward node, this is forward list, do you see it? Considered declared. And this is why inside the class body we can use a pointer or a reference to the class itself, like this one, even though the class is not yet fully defined. At that point, the compiler treats it as an incomplete type, which is sufficient for declaring pointers. Now, a little challenge. Who can spot how to save 3 characters in this code? Remove 3 characters and make this code the same. And we can indeed save those angle brackets t by writing just forward node pointer next. This is exactly equivalent to forward node square brackets t pointer next when used inside the class body. This is a convenient shorthand the language provides. You can omit the template arguments when using the class's own name inside its body. I'm sure you've all wanted to see this technique. It makes the code much cleaner, right? For example, in a class like stack, you could simply write forward node pointer top instead of the more verbose version. And looking at this stack implementation, it doesn't seem very efficient for storing simple types like integers, does it? We're dynamically allocating a small node for every single integer we push onto the stack. That's a lot of overhead for a type that could potentially be stored much more efficiently. So what can we do about it? This is a perfect moment to discuss how we can optimize our template design. What are your thoughts on how can we improve it? And of course, this stack is inefficient, and for a general type T, we need a flexibility of node-based allocation, but for a simple type like int, you could use a much more effective implementation like a dynamically growing array. And this is perfect job for explicit specialization. Like in function case, we can keep the general template for int type T, but provide a completely different, optimized implementation specifically for int. Here, the specialized class stack of int replaces the linked list of nodes with a contiguous array. This will be far more efficient for storage and access. And the interface in this case remains same, but for specializations, even interface can change. And we can create explicit specialization for a class just like with function, and instantiation also generates a specialization for us. The same core mechanism applies to classes, and the same critical rules applies. If specialization has been already implicitly generated by the instantiation process, we cannot later provide an explicit specialization for it. It already was introduced. So, if we write an explicit specialization first, the instantiation will simply use our handwritten version. But if the compiler generates one first, we cannot provide our own. Now, here's an interesting question. What if we don't want to specialize for just int, but for a whole category of types like all pointers? What do we do then? And For functions, if we wanted to handle pointers specially, what would we do? We would simply create an overload, perhaps using a requires clause to specify that t must be a pointer. But for types, we don't have overloading. So what's the solution? Partial specialization. This is how we tell the compiler, use this different optimized implementation of stack not for one specific type like int, but for any type that is a pointer. Int pointer, double pointer, my class pointer, you name it. Here we've partially specialized this stack of t pointer. The primary template still handles all non-pointer types, but for any pointer types, the compiler will use this more efficient version that stores a plain array of pointers. This is a powerful technique that's unique to class templates. And what's particularly interesting is that the name simplification we saw earlier works just as well inside partial specializations. Now we are saving a whole 4 characters. Notice that here A means A of T pointer. And sure, everyone who knows this rule understands it, but it does rely on everyone reading the code having this specific knowledge. Using the full explicit name here, like A angle brackets T star, is perfectly legal and is often a much clearer and safer idea. And I hope a partial specialization seems straightforward so far. We have our primary template full, and then several specializations for specific patterns. It also looks simple, same types. One type nailed down to be int, other type like every type. Both types nailed down to be pointers, and this binds to 1, this 2, this 3, and this is 4. And please don't ask me what happens with something like fourth int and int. By the way, what do you think? Which one is more specialized? The one that fixes parameter as an int, or one that requires both types to be the same? How do we determine the order? And this is exactly what we'll explore next. But think about it. We've already seen ordering everywhere in C++, between concepts, between function templates, so on. In C++, there's ordering everywhere, and that's a good thing. This means a language has a consistent set of rules. And now, for a small shift in perspective, we can create specializations based on elaborated types. This means we can write a partial specialization that matches not just simple categories like all pointers, but complex patterns. And here we have primary template and a partial specialization for all that looks like vector of t. By the way, do you understand why stud vector will not match here? Okay, I hope you do. And when we create a specialization, it must satisfy a k condition. It must be strictly less general. Okay, ordering again, strictly less general. Then the template, it specializes. If we try to write something like this, it is an error. Please note, it is not an error. It is an error. This partial specialization is exactly as general as the primary template. It matches every single type U, just like the primary template T does. It doesn't specialize anything. It's just redundant. So what does less general actually mean? It means the specialization must match a subset of the type that the primary template matches. And a specialization that is more specialized can have even more template parameters. Look at this. X specialized for all function types, and it introduces 2 parameters. It matches all functions taking a single argument. the primary template is more general, and this one, despite having two template parameters, is more specialized. How should we think about this? The specialization must consume all the template parameters of primary template in one way or another. And then it's free to introduce as many new ones of its own as needed. And this makes it more specific if it consumes something more specific than general parameter. And because the primary template accepts any t, while this one only accepts types that look like a function with one argument, this is more specific. But how computer will understand it, how compiler will understand. And we already have many mechanisms in C++ that we've reused multiple times. We reuse type deduction for more general, more specific function templates. How can we formally determine which template is more general by reusing something? Please think about it. And we can establish a partial order for class template specializations with brilliant trick. We pour the water out of the kettle and reduce the problem to a previous one we've already solved. We invent function templates. For each class template specialization, we create a corresponding function template that takes this invented type as its parameter. Once we have this function template, we applied our favorite cross-type deduction, the same partial ordering rules we use for function template to determine which one is more specialized. And that's how it all comes together. We reuse a well-defined mechanism to solve a new problem. So to summarize the restrictions, a specialization must always come after the primary template. Of course, primary template must be reachable from the point of specialization. This was after means. And it must be strictly less general than the template it specializes. And now, key limitation, full specialization is allowed for both classes and functions, and partial specialization is not allowed for functions. This will fail miserably. And if it is not allowed, how will we hack our way out of it? Pause the video now. Can we mimic function partial specialization using a different feature? 3, 2, 1. Okay. This trick was proposed by Herb Sutter in 200, was beginning of the 21st century. It is classic workaround. The problem is we can't partially specialize a function template, but we can partially specialize a class template, and the trick is to delegate real work. The beauty is that now we can partially specialize this class for any pattern we want, like for all pointers, and this effectively gives us partial specialization of this function because it delegates to partially specialized static member function. And the main technical difference is that a static method doesn't do template argument deduction for its class. But that doesn't matter for this trick. This is subtle difference, but the trick works perfectly. And we are nearing the end with a simple task. I'm sure you can all handle this one easily. Here's a challenge. We have something like data struct with a templated read method, and we also have a data reader class template with its own templated read method, which should call source.read. And your task is to define data reader : read here in this point, not inside the template body. Pause the video now and write it on the sheet of paper. How would you do it? And then proceed to the next slide to count your mistakes. First attempt here, note template here and template here. It's not a typo. It's not a typo. And probably you did something like this, and this is wrong. This is syntactic ambiguity. Who can spot what the ambiguity is? Of course, of course. This is less if we will not disambiguate it with template keyword. And this was simple, I believe. A more complex task is to write an explicit specialization of read function specifically for std_string, for r equal std_string. How would you do this? And again, please pause the video, take a sheet of paper, and write it down. 3, 2, 1, okay. You probably did something like this, and this is blatantly wrong. Our first instinct must be to write something like this, but we are trying to use void angle brackets for the member function, thinking we are fully specializing it for std_string, but this code doesn't compile because this is a partial specialization. This function really have two template parameters in different but nested template parameter scopes. Do you remember about scopes? We did have template parameter scopes. Okay, here it is. And the correct answer is that this required specialization is not possible at all. What we are attempting here would be a partial specialization. And partial specialization for function templates, including member function templates, is simply not allowed. However, there is a way. If we lock down both templates, if we have a concrete data type, we can write a full specialization for a specific instantiation like data reader, data read string. And the general case we were aiming for remains out of reach. But how will we write this? And this is simple. This is the syntax for a full specialization of a member function template. Notice the double void angle brackets. The first line template empty angle brackets specializes the entire class data reader for the specific type data. The second template then specializes the member function template read for the specific type string. And this is only possible because we have fixed both template parameters. The class template parameter t is fixed as data. The member function template parameter r is fixed as string. And this creates a fully concrete non-template function. Now, this is a very specific solution, but it's the only way to explicitly specialize a member function template from outside the class. And now we know a lot about our semantic process. Let me show you. We are starting with name resolution. Aliases vanishes somewhere here, and we might proceed to type deduction or to type substitution. After type substitution, second phase of name lookup may happen. After type deduction, type substitution may happen. In the process of type deduction, second overload resolution may happen, but not returning to type deduction. And this is where metaprogramming blocked. After type substitution, constraint check might happen, but not constraint of constraint of constraint. And this is where type class-based metaprogramming is blocked. And after type substitution or after type substitution and constraint check, template instantiation can happen. And this is the only allowed form to cycle this process. And this picture looks like purely unnormal process, but this is a general one. And this is why I'm saying if you do have normal process in your program, it's fine. You did a great job. Your program is simple, readable, conceivable, supportable, naked. Okay, and it's tempting to go this remaining arrow, to follow it and begin and start it over again. But the next lecture, and probably maybe the next after next, we will talk rather about what this big before after means and about physical structure, and we will follow this arrow later in this course. And now homework assignment. For your homework, I want you to analyze this code according to the C++ standard, and your task is to determine if this code is well formed and to explain why or why not. Students will send me their homework, and because the deadline is 1 month and this lecture will appear on YouTube 1 month later, you may safely post it in comments and be the first to solve it in comments on YouTube. Pay close attention to parentheses around foo and what that changes. And second homework assignment is writing a permanent set. Refer to great book of Corman on algorithms where this permanent set task is explained. And I just note here that this is input from student input, like scene, and this is adding a key, and you're adding a key just to search tree without balancing, and this as command creates a version, and you supporting only one version at a time, and this rollback command rollbacks a version. Try to use your knowledge of template programming, of generic programming, to design good generic class for the permanent set. This is not so easy as you can think. And a brief literature overview. Today's list is quite amusing because it's almost entirely made up of talks titled Back to Basics. CVPCon has this great tradition every year. They accept another talk that once again explains templates, and it's almost always called Back to Basics. Dan Sachs did Back to Basics in 2019. Then in 2021, Bob Stigl did a two-part Back to Basics template, and in 2022, Nika Yasutis did Back to Basics templates. And if you've ever seen anything by Nika Yasutis, you probably don't believe it's a basics talk. And you're right not to. From this list, I would watch Yasutis first, but you might achieve a truly enlightened understanding if you watch them all in order, starting with Walter Brown's talk from 2018, which is also basics talk, though he didn't call it that. By the way, Walter Brown is the author of the D programming language. What is the author of the D programming language doing at CPPCon at 2018? Okay, that's right, given a fantastic talk. If you do this, it like watch this and then this and then this and then this, you will spend like about 7 hours. And it might cause a real paradigm shift. Templates in the C++ programming language could become completely clear to you. And if you read the C++ template book by Van der Voort and Yasutis alongside these videos, you can get really deep understanding. All right, that's all for today. I'm still looking forward for your brilliant submissions of homeworks in the comments of previous lectures, because all deadlines are passed for students, and you, my watchers on YouTube, may enjoy this homework. And that's all for today. Thank you, everyone.